Dr. Amir Hashemi is a leading person in the computational algebra and algebraic geometry in Iran. I don't know if he remember, but at early 2015, I wrote an email before I start my PhD in Copenhagen to him asking for an appointment to meet him in Isfahan. And he agreed. But then I found that other topic which become my PhD things, and then I lost the interest from this side to move to the other side. The appointment got canceled. I couldn't see him in person, but now I'm lucky enough to see him online. So, Dr. Hashemi, please start there.
Yeah, thank you, Amir Hussein, for the introduction and also for the invitation. It's a pleasure for me to give a talk here in this event. I will talk about the complexity of the saturation of third-dimensional ideals. And this is a joint work with my PhD student, Fatima Akbari. The slides changes correctly?
Yes.
Amir Hussein? Yeah.
Yes.
As the outline of this work, I will I'll give you a short introduction about the subject, about also grammar bases, and also introduce the saturation of polynomial ideals. I will talk about a hidden algorithm in literature, so-called traversals algorithm. For me, is an interesting algorithm, and I'm happy to discover this algorithm from a hidden book also. And I will talk about the application of this algorithm for the saturation of ideals. As an introduction, I can talk about grammar bases, an interesting concept in computer algebra, which has been introduced by Bruno Buchberger in his PhD thesis. And also the first algorithm has been given in his thesis in '65. And these bases have many applications in mathematics and also outside mathematics. And in particular, in algebraic geometry, it has many applications, including the computation of the saturation of an ideal. If you are not familiar with these bases, also not with saturation of an ideal, I will talk about them in details. I will introduce you these notions. But in particular, I'm interested in the saturating a zero-dimensional polynomial ideal with respect to a given polynomial f. And I use linear algebra techniques and also this hidden algorithm. And I will talk about the complexity of this approach for this computation. And also I will show the performance of this new algorithm for this computation. As the notations that I use throughout this talk, K stands for a field, and also P is the polynomial ring in terms of these variables. And for me, a term is a pure power of variables. And also this notion prec is a term ordering. You can consider, for example, lexicographical ordering to order the terms in this polynomial ring. And also a polynomial is a finite linear combination of terms. An ideal I for me is an ideal generated by some polynomials in P. Once you fix term ordering in this polynomial ring, if f is a polynomial, so the highest term in this polynomial is called the leading term of f and is denoted by the LT of f. So it does not contain the coefficient C alpha. It is only the pure power product of variables. We can simply now define a Gerber basis, so a finite set G1 to Gt of I of non-zero polynomials forms a Gerber basis for I if the leading term of these polynomials are enough to generate the leading term ideal of I, this ideal. One of the main properties of Gerber basis is that if you are given a polynomial like f, the remainder of f by a Gerber basis, here should be I, is a unique polynomial. We call this unique polynomial, we call it the normal form of f, and we denote it by nf of subscribed g of f. If you have any question, please interrupt me and ask your question. As a history, so we have first the works of Buchberger on this subject in 65, the definition of the concept and also the first algorithm. Then 14 years later, he introduced two criteria to enhance his algorithm. And in 88, Gebauer and Müller installed this criteria on Buchberger algorithm in an efficient way. We have the work of Forger and his colleagues, so-called FGLM algorithm to convert a Gerber basis from an ordering to another one. And also we have the famous algorithm by Jean-Charles Forger, F5 algorithm, which is the most efficient algorithm for the computation of Gerber basis. I would like to mention also a work by Berkesh and Schreier in 2015, which presents a simple and efficient presentation of Gebauer and Müller algorithm. I invite you to have a look at this algorithm and to understand it. It is an interesting algorithm. An application of Gerber basis related to the subject of my talk is about the quotient of rings. So if you are given an ideal I, we define an equivalence relation on P. So two polynomials are related if their subtraction is belongs to I. So we can define the class of F, which is the set of all polynomials related to F. And P over I is the quotient set, which is the set of the class of all polynomials in F. This quotient set has the structure of a ring, and at the same time, it has the structure of a vector k-vector space. And we call it the quotient ring of P over I. So the natural question that Buchberger answered in his PhD thesis is to find a basis for this quotient ring as a k-vector space. I give answer in this slide. So for this purpose, you need a Gerber basis for I with respect to any arbitrary term ordering. And also he showed that we have this isomorphism between these two quotient rings, where here we replace it by a monomial ideal. So we can reduce this computation to this computation, which is the quotient by a monomial ideal. Furthermore, we define the notion of the normal set of G is a set of all terms outside of this ideal. So this are all terms which are not in this ideal. This set is called the normal set of G and is denoted by N of G. And there is a famous theorem in capital algebra, which we refer to it as Macaulay theorems, and it says that the set of the classes of these terms from N of G forms a k-vector space for P over I, and it is one of the main theorem in Buchberger's PhD thesis. And from this also we have a classification or definition of zero-dimensional ideals. So an ideal is zero-dimensional if and only if this normal set is non-empty and finite. For example, as a baby example, if I is this simple ideal, this generating set forms already a Gerber basis for I, and the leading term of I is generated by these two terms. So we have this isomorphism between these two vector spaces. And N of G is a set of these four terms, and the class of these terms forms a Gerber basis for this set as a k-vector space. And so we can say simply that I is a zero-dimensional ideal because this set is finite. And this view and this indeed brings linear algebra into computer algebra. What about the saturation of ideals? Again, assume that we are given a polynomial f inside P, and also an ideal I. We can define the colon ideal, or sometimes it's called quotient ideal of I by f, and it is the set of all polynomial G inside P such that f times G belongs to I. we have simply this chain of ideals. So I is a subset of I 2.f, f squared, and so on. And by Newtonian property of P, we can show that, we can see that this chain is stationary and it stops at some ideal. Here, for example, at this place it stops where we have this equality. And exactly the place that it stops is called the saturation of I with respect to F. So we define it as A 2.F infinity. It is equal to I 2.F to S. And this ideal is called the saturation of I with respect to F. We can define certain different notions of saturation with respect to, for example, an ideal, and all of these computations come back to the computation of I 2.F polynomial. So it is crucial that we have and we find a good algorithm for the computation of the saturation with respect to only a simple and single polynomial. And the smallest number s such that where this chain stops is called the saturation number of I. And it's a challenging problem in computer algebra to compute the exact value of the saturation number given an ideal I and a polynomial f. A traditional way to compute the saturation of an ideal is by a Rabinovich trick. Is a perhaps shortest paper in literature, half of page. You can find it, this simple trick. And by this trick, consider an ideal I and polynomial f, and we construct a new ideal I, a new ideal j by adding this new polynomial to I, where w is a new and tag variable. Then it is shown that the saturation of I is the intersection of this ideal by the polynomial ring P. So by using the elimination theory and Germer basis, as explained here, we are able to compute. So if you compute just Germer basis for this ideal, and you intersect this Germer basis by P, you get a Germer basis for the saturation ideal. On the other hand, if you compute this set G, its Gi can be represented as a combination of F1, Fk, the generator of I, and also this new polynomial. Assume that S is the maximum degree of W in Hij's, then S is an upper bound for the saturation number. It is not the exact value for the saturation number. Let's see a simple example again. Assume that we are given this ideal I generated by these three polynomials. Assume that F is this simple term. So we construct the ideal J constructed by these three polynomials, and by adding this new polynomial to this ideal I. If you compute a Germer basis for J with respect to, for example, next ordering, you get these three simple polynomials. So if we intersect it with P, I mean K of X and Y, you get these two polynomials, and this forms a Germer basis for the saturation ideal. Now, if you write this element of Germer basis in terms of F1, F2, F3, and this new polynomial, you get this representation. And you see that the highest degree of W here is 3. And it is the same for 1 plus X. So we conclude that 3 is an upper bound for the saturation number. And we can see that the exact value is 2. So this way does not give the exact value of the saturation number. I don't explain it here, but in our paper with Fatemeh, we show an approach also to compute this saturation number, the exact value of this saturation number. What about the traversals algorithm? What is the purpose of this algorithm? Assume that you are given a zero-dimensional ideal I and also a Gerber basis for this zero-dimensional ideal. So it is can be computed in an efficient way. And also assume that we are given a polynomial f. The goal is to update this Gerber basis G by adding this polynomial f. I mean, how we can use G and f to compute simply a Gerber basis for I plus f. Carlo Traverso, a well-known mathematician, Italian mathematician, presented a simple algorithm unofficially at the conference Mega in '92, and later Theo Mora reformulated this algorithm in one of his books in 2005. Here I give, in a non-accurate way, the presentation of this Traverso's algorithm. So I assume that we are given a Gerber basis, a polynomial f, and also a term ordering. We would like to compute a Gerber basis for this updated ideal. So H for me is the set of new polynomials that we compute during this algorithm, and P. So at the end, I return G union H, and P is the set of polynomials to be studied. So in some sense, H is the set down and P is the to-do set. While P is not empty set, so we select and remove a polynomial from this set of critical pairs, I can say, then compute the normal form of this polynomial P with respect to the given Gerber basis. We compute this normal form, and then we reduce this polynomial if it is not zero. If it is not zero for this case, for the initial case, we compute its reduction with respect to this set H. If it is not zero, then I add these multiplications to P, and also I update H by adding P to it. And finally, I return G union H. It's a simple presentation, but in the book by Mora, you can see a more complicated presentation of this algorithm, but really, this presentation is not really efficient, but just I gave this presentation so that you understand the main idea behind this algorithm. As a simple example, I explained just one or two steps of this algorithm. So if G is given and f y squared is given, then this ordering, H at the beginning is empty set, P is y squared. So I compute the normal form of this polynomial, which is minus y. I add minus y to H, and the multiplication, all multiplication is minus y to P, and again I compute. Here you can see the procedures, and at the end I obtain the updated Gerber basis. In our paper, we gave a rigorous proof for the correctness and termination, and also for the complexity of a traversal algorithm. One of the questions that we addressed in this paper is how we can combine this algorithm with a new algorithm, so-called F5 algorithm. Perhaps you are not familiar with this algorithm, but here I give a general view of this algorithm so that you get the main idea of this structure. So indeed, F, so we are again in the setting of Traverso's algorithm. We are given a Gerber basis and a polynomial. So for me, F is the root of any constructed new polynomial. At the beginning, instead of representing F, I represent it as a pair of a term and a polynomial. So at the beginning, this term is 1. So it means that this polynomial f comes from 1 times f. And in the course of the algorithm, also each polynomial is represented by this pair. So P is the polynomial exactly, and it is also attached with a term T. And It means that this polynomial P comes from the reduction and the successive reduction of T times F. So this T, by the paper by Fauger, it is called the signature of this paper. And P is called the polynomial part. So in some sense, this signature allows me to keep the track of the computation and to see from which multiplication this polynomial P comes from. Given this structure, we have this kind of criteria presented in the Fauger algorithm. The first one is rewriting criterion. Simply, it means that if you already computed, for example, this pair, if you meet again a new pair with the same signature, so you can remove simply this new polynomial. So no duplicates in signature. If you compute a polynomial pair such that P is equal to 0, so I add T to the syzygy criterion, it means that later I don't need any multiplication of T. They also reduce to 0. And also, if you have a pair such that T belongs to the LT of G, it is superfluous and you can remove it. So we can simply modify the traversal algorithm by this new structure. So instead of saving F, I use this pair. Again, here I choose a pair with a pair in P with minimal signature. So I look this part only. And again, if I want to update P, I add all these multiplications, these pairs to P. So it is really not much work to do to have this new structure. And we have implemented this algorithm in Maple, and we can see that mode traversal algorithm is really faster here. This column shows the timings for some examples. Some of them are well-known examples from literature. And you can see the difference of timing in all examples for the computation of the Gerber basis. And arithmetic complexity, we showed that of this new algorithm is n the cube, which is exactly that complexity of FGLM algorithm. Now, how we can apply this structure for the computation of the saturation of an ideal. As you've seen is in the Rabinovich trick, to compute this saturation, we need to add a polynomial into I, into an ideal I, where I is a zero-dimensional ideal. So if we are given a Gerber basis of I, indeed, we can use traversal structure algorithm to update this Gerber basis by adding this polynomial. But it is not really a simple task. We need to state and prove some result that we can do this structure. So I explain this approach here using Rabinovich trick. If we are given a Gerber basis for I, and if I is zero-dimensional, so we want to compute a Gerber basis for updating I by adding this new polynomial. And so we can apply traversal algorithm. We need to prove some results. For example, the simplest one is to show that this algorithm, this ideal is again a zero-dimensional ideal. Also, we show that any polynomial raised in this computation is linear in terms of W. And also, we need a slight modification in traversal algorithm. If W does not divide, only in this case, we add this multiplication to P. If not, we just update it by multiplying by x1 till xn. So all this stuff have been proved in the paper, and we implemented the algorithm. So since I don't have much more time, so I just explained you that the new algorithm is much faster then applying a traditional algorithm like, for example, Berkshire algorithm directly if we apply it by using Rabinovich tree. As the perspective of this work, so we can think of how we can generalize traversals algorithm for positive dimensional ideals, perhaps in a generic position like neutral position. How we can use it for the computation of primary decomposition, because this notion of saturation of ideals is an ingredient for the computation of primary decompositions. How we can use this structure for the computation of evolutive basis, and what about applying this algorithm in non-commutative setting? So thank you for your attention. I hope that I was in time.
Okay, yeah. So is there any questions from the audience? We have 4 minutes time for the questions. If you have a question, raise your hand and we call your name. You can unmute yourself. Ask. If you are shy, you can type in the chat. If there is no question, I can ask some quick question. I picked up some note on the question things. I will ask that later. But, well, okay, Said has a question. Said Qurbani?
Hi, can you hear my voice?
Yes.
Okay, thank you, Dr. Hashemi, for your presentation. And my question is does your method also work when we add some finite number of non-zero polynomial to the Grobner basis?
Yeah, good question. Yes, of course. And instead of adding one polynomial, you can iterate this approach by adding one by one the polynomials. And if you would like, you can add also at the same time all the polynomials. If I go back to, here, instead of charging P, but only one polynomial, you can charge it by F1 till Fk. And then you can continue exactly the same way. But we can do it also iteratively, and we tested both of them. And if we add iteratively the polynomials one by one, it is faster.
Thank you.
You're welcome.
Okay, any other question from the audience? Okay, so my question would be a bit general about the Grobner basis algorithms, because I saw name of several of them there. Can I ask, which algorithm do you think is the state of the art right now? I heard that, for example, in Maple, they do the Grobner basis in graded reverse lexicographic, and then they do random walk to convert it to other orders. But for that graded reverse lexicographic, which of the algorithms they use to calculate the Grobner basis?
In Maple, as far as I know, they use the F4 algorithm by Jean-Charles Fougère. When I was a PhD student at the team of Fougère, they gave their package of FGP to Maple, and at that time, I don't know if they have updated this computation or not, but I know that at one time, the algorithm by Fougère has been introduced in 1999. A F4 algorithm is the main engine for the computational Grobner basis in Maple. But not the case for example, in Singular. I think they used the traditional work by Gebarn and Müller algorithm, but in a very, very efficient way. And this implementation also is very efficient in practice, Singular one.
Thank you. I think it's 8 a.m. in UK time. We have to move to the other one, but maybe I can use this reaction of clapping for thanking our speaker. It was a very